Ali Yazdani, if you meet somebody at a party and this person asks you, Ali, what is your profession? What is your answer then?
Well, I'm a physicist and I study what electrons do in interesting materials.
Okay, and what is an interesting material? The person asks.
So materials are basically, you can think about it as divided into categories in which we can understand based on simple quantum mechanics, like simple insulators that don't conduct electricity, simple conductors like a piece of copper, and then there are other materials that have properties that requires quantum mechanics to understand why they do what properties they have. And I study them for a variety of different reasons, but understanding what electrons do in materials, it's kind of like thinking, how could we live if we lived in a different universe? You can manipulate the rules of quantum mechanics inside materials in a ways that we cannot manipulate the rules of the universe, the one we live in.
So this is a complete different universe, it's a complete different physics? Is that
no,
true?
It can be the same. So electrons, for example, in materials can behave like tennis balls that you have in our everyday experience. But it can, because of quantum mechanics, and inside materials, because the rules of quantum mechanics depends on what atoms you have and how they're connected, what crystal structures you have, and so on, you could actually change the rules. But you can use the same mathematical structure that we have developed to understand our everyday experience and also quantum mechanics in sort of our universe, but also apply to a very specific set of situations in which you have subjected electrons to in a material.
Give me a nice example. What is a behavior of an electron that is different in classical physics and different in the field you work? What?
So the simplest example is a superconductor. A superconductor is a state of electrons inside a material in which the electrons flow collectively without any electrical resistance. So the copper wire that you use in conducting electricity in our house has resistance. And that resistance comes from basically electrons bouncing off of the defects of the material or bouncing off of even each other. But the state of matter called a superconductor is one that forms when electrons collectively exhibit a quantum behavior in which they will flow together without any resistance. And that's probably the most magnificent example of a collective and quantum phenomena that is very different. Because if you make a circle of electrons in a loop, they can just go around forever.
This would be the perpetuum mobile, so to say.
That's right.
And the detection of then it was a world record in a high temperature superconductivity, which was invented by two Swiss
That's right,
researchers.
Bertels and Miller. Yes.
Yeah, and they won a Nobel Prize afterwards. And I interviewed them, and they told me, well, we were calculating and we were thinking a lot about the materials that we mixed together to see which materials that are hard, that are real world, but have a strange behavior. But at the end, what came out was kind of coincidence.
Well, serendipity has a lot to do with discovery in science. But, you know, if you go looking for something and you have the right tools and you have the right nose, sometimes even if you can't calculate, you know, human ingenuity, as that example shows, can lead to discovery. You can't tell how you get there, but that's what part of science is about. Some is trial and error. Some things become precise enough that you can compare to theory. Sometimes theory makes a prediction of where to look for an exotic phenomena, and they don't have the right idea where to look for it, but just knowing that idea could happen can lead to you looking for it in an unexpected place, like that example.
And sometimes the theory and the experimental proof can be 40 or more years, like the Higgs boson, for example. It was predicted in the 80s and just a few years ago discovered.
So precisely, actually, the areas that I work in are the cases in which you cannot calculate, because the quantum problem is so complex, you need a quantum computer to solve it, which we don't have today.
So you can't solve it? You say you need a quantum computer to solve it, which we don't have. So you ergo.
So this is actually one of the things that was motivated the field of quantum information, quantum computing to begin with, which goes back to Richard Feynman, the American physicist who thought about what it would be like to think about quantum mechanics and computation. And in fact, one of the first things he said was that if you had a quantum computer, the first thing you would try to do is ask it to simulate a quantum problem, which is what it would be most useful for. So the set of physical problems that happens in real materials that I work on are ones in which you cannot ask a theorist to calculate. They will make a lot of assumptions that will give you a recipe. That's where I'm an experimentalist. So doing an experiment is what becomes the way you do science in those areas. And there is a feedback between theory and experiment once you have experimental results and following some predictions by theory, but there is not. It's not easy.
I hear you prefer being an experimentalist than a theoretical physicist.
Well, I actually started as a theoretical physicist, but
now the experiment is part of your daily work.
Yeah.
You mentioned you are working in a two-dimensional room, or I cannot imagine what is two-dimensional because the world is three-dimensional.
Sure.
And even an atom has three dimensions. It has a height and a width. And what is a two-dimensional scale? What is this?
So, you can think about basically, when you think about particles, you think about what describes them in quantum mechanics is a de Broglie wavelength. It's a quantum mechanical wavelength which describes where this particle is, and also the wave function, which if in quantum mechanics, if you don't measure the wave function directly, but you measure the probability distribution that's predicted by quantum mechanics in the wave function. Now, when you create physical situations in which electrons' motion in one dimension is so confined that you do not need to prescribe that degree of freedom in your description of that state. It could still have a thickness, but you do not need to take into account them moving in that direction.
Two-dimension means no thickness.
Yes, exactly. So it could So we are working with materials that are one atom thick. Mm-hmm. For example, like graphene was isolated, in 2004. Mm-hmm. But electrons, of course, are leaking into the vacuum, if you wish. Mm-hmm. But for description of their motion, you do not need to describe that degree of freedom. You just need to describe the degree of freedom in the plane of the material. Okay. And that's a way in which you can think of it as two-dimensional.
Mm-hmm. And you work with layers so thin, only 2 atoms thick.
Yes.
And this is really, really, really thin. But why is your work important?
That's a good question. So what I do is in my laboratory, we have developed specialized instruments, which with these instruments, we actually measure where the electrons are. Mm-hmm. Okay. The way this instrument works is we bring a sharp tip and you tunnel. This is actually another instrument that was invented in Switzerland.
And another Nobel Prize.
And another Nobel Prize.
And the Nobel Prize laureate lived in the same town as I do, in Winterthur.
Okay. Yeah, the scanning tunneling microscope, which was invented by Binning and Rohr. Mm-hmm. And basically, this is a very... we have turned this tool that was initially intended for just imaging atoms into a tool in which we can ask what electrons are doing, just not in space, but in the energy landscape.
Okay. More for lays. Why do I have to know where these electrons are?
Well, basically, what we were trying to do in these two-dimensional materials is create state of matters in which you can encode quantum information in new ways that is very protected. Now, to know that you have created these states of matter, you need to make some experimental measurements. And there are experimental measurements you can do that's macroscopic. You measure the resistance through the device and so on. But what we really want to do is we want to interrogate them more precisely to actually not only just see the electrons that are doing this interesting quantum state, but actually to utilize them in new ways to encode quantum information. Mm-hmm. For that reason, we need tools which actually gives us a window into what's happening in the microscopic world, on the scale of the electron wave function, on the scale of atoms. And that's why the instruments that we build are particularly useful, because it can give you a picture of what is happening on a scale that you care a lot about and you want to manipulate this quantum state in. So that's what makes our tool particularly useful. And these two-dimensional materials are are providing some very extremely clean material platform, free of atomic defects and so on, in order to create some rather exotic quantum states. So my lab kind of combines the two together, sort of using these two-dimensional materials and using these high-resolution tools. It's like a high-resolution camera for catching the quantum action.
So summarizing, you are not developing the quantum computer, but you are developing methods and materials that allow others, perhaps generations after you, to develop the quantum computer.
So right now, the quantum computing community is focused on using materials, quantum phenomena, to create qubits based on physics concepts that would be 20 or 30 years ago were developed. And these qubits have some intrinsic noise issue, which has to do with the fact that how they're encoding quantum information. What I'm working on is quantum states that our understanding of which is just developing, but we expect us to be able to encode quantum information into them in much more protected way, in a way that make a much better qubit. But we haven't made a qubit yet.
Yeah.
What we are working on is the science behind it. And from a scientist's perspective, the discoveries we were trying to make and understanding of phenomena we were trying to make are so interesting. I think quantum computing would be a bonus. But in this case, the science is actually quite exciting.
Mm-hmm. Yazdani, I thank you very much for this interesting talk. And I hope you find that qubit that helps the quantum computer to be born.
Okay, thank you.